On a clear night, the stars appear as fixed, reliable points of light. But under specific conditions, an observer might watch them warp and vanish one by one, leaving behind a widening void of absolute blackness. This occurs when a massive object moves directly between Earth and those distant suns. It is a mass so dense that it prevents the escape of all light and radiation, moving through the vacuum without a trace. These anomalies are called rogue black holes. While most black holes remain anchored at the center of a galaxy, these examples have been detached from their original coordinates. They drift through the interstellar medium without a fixed orbit, meaning they occupy the same galactic volume as our own solar system. Their journey begins in chaos. When galaxies collide or stars collapse into a supernova, the resulting gravitational energy can act as a slingshot. This force ejects a black hole into the void at speeds reaching millions of kilometers per hour. This view of the Milky Way represents a vast, crowded neighborhood. Astronomers estimate that within these spiral arms, approximately 100 million rogue black holes are currently in motion. Evidence of their existence was confirmed by the Hubble Space Telescope. In 2022, Hubble identified OB110046, a black hole drifting independently through the galaxy. This specific anomaly was detected 5,000 light-years away. While that distance is vast, it confirms that these objects are not limited to the distant universe. They are present in our local stellar environment. The Milky Way contains billions of stars and immense stretches of empty space. However, over billions of years, the probability of a rogue mass crossing the path of a star like our Sun becomes a statistical eventuality. The entry point is the Oort cloud, a spherical shell of icy debris at the Sun's outer edge. As the anomaly enters, its presence is revealed by the severe warping of space, its mass redefining the outer solar system's physics. The gravitational influence of the black hole acts on the Oort cloud like a rake. It violently disrupts the orbits of millions of dormant icy bodies, pulling them out of their stable positions. These comets are slingshotted toward the Sun, creating a sudden influx of debris that accelerates toward the inner planets. The arrival of this comet storm serves as the first measurable evidence of the black hole's approach, long before the mass itself can be localized. As the anomaly continues inward, it reaches the orbital planes of the gas giants, where the scale of disruption increases. This diagram illustrates the orbital mechanics of the encounter. The gravitational pull of the passing black hole begins to override the Sun's hold on the planets, forcing their stable, circular orbits into erratic and elliptical paths. For a planet like Neptune, the encounter could be terminal. If the black hole passes close enough, Neptune would be stripped from the solar system entirely, becoming a rogue planet in the interstellar void. Saturn faces a different catastrophe. The tidal forces generated by the black hole would destabilize the gravitational balance that maintains its ring system, causing the rings to disperse or collapse. Before the black hole reaches the inner solar system, the orbital architecture that has remained stable for 4 billion years would be fundamentally dismantled. When the focus shifts to Earth, the physics of the encounter become more personal. A direct collision is unnecessary for total biological extinction. A near miss is sufficient. This cross-section shows the effect of tidal disruption. As the black hole passes, the planet's solid crust and iron core are subjected to immense competing gravitational pulls. The Earth itself begins to stretch and bulge toward the passing mass. This internal distortion generates heat and mechanical stress. Tectonic plates that move millimeters per year would suddenly shift kilometers in hours, triggering global earthquakes and volcanic activity. This image of Earth highlights our oceans. The black hole's gravity would pull these waters out of their basins, creating surges that submerge coastal regions and move deep into the interior of continents. Biological survival is impossible under these conditions. Human extinction would be the result of gravitational mechanics, not a sudden explosion. While Earth's fate is a consequence of the black hole's path, it is not the only planet at risk. Jupiter, the largest planet in our system, presents a massive gravitational target. How would its vast atmosphere react to the presence of a rogue black hole? To understand the mechanics of Jupiter's destruction, watch the next episode, The First Sign, Why Our Outer Planets Would Disappear First. Subscribe to follow this series as we map the end of our solar system.